this video, we're going to look at non-standard normal distribution applications. That is, variables that have a normal distribution, but either the mean's not 0 or the standard deviation is not 1. So for our first example, okay, the time it takes a UT student to travel from HSS to the Ag campus is approximately normally distributed with a mean of 11 minutes and a standard deviation of 5.2 minutes. Okay? And we want to know the probability that a randomly selected student travels to the Ag campus in 16 minutes or less. As with all continuous distributions, first thing we're going to do is draw the graph. We have a bell curve because we're normally distributed. The mean is 11. We want the probability that the time to get to the Ag campus is 16 minutes or less, so we're going to shade in everything to the left of 16 minutes. Okay. And to find this area, we're going to use our normal CDF function. Okay. So the probability that x is less than 16, the time to the Ag campus is less than 16 minutes. Okay. So we found using the normal CDF, we got to put our lower and upper limits in, our mean and our standard deviation. So we're going to go from negative infinity up to 16 minutes. Okay, put in our mean and standard deviation of 11 and 5.2 respectively. And we end up with a 0.832 probability that a randomly selected student will take 16 minutes or less to get from HSS to the Ag campus. In this example, we're still talking about the amount of time it takes to travel from HSS to the Ag campus. Okay. But now we want to know how long do the slowest 10% of students take to get from HSS to the Ag campus. So this is a percentile problem, not a probability problem. So I'm going to start by drawing the graph. Okay, again, normal distribution, normal curve, centered at 11, the mean. We want the slowest 10%, so they're going to be slower than average. Okay. So we need the area to the left to be 0.90. Okay. And so that is going to come back at 17.664 minutes. And so 90% of students, all right, can get there in 17.664 minutes or less, but the slowest 10% take 17.664 or more. So let's look at a completely different variable. In the amount of weight in a UT student's backpack. Okay, so we're going to assume they're normally distributed with an average of 18 pounds and a standard deviation of 3.2 pounds. So we want to know what is the percent chance that a randomly selected student's backpack is more than 25 pounds. Again, our weights of backpacks are normally distributed. We're going to start by drawing our normal curve. We want the probability that we have a backpack that weighs more than 25 pounds. So we need to find the area to the right of the 25. We're going to do this with the normal CDF. Again, lower, upper, mean, and standard deviation. So in this case, we're going to go from 25 to infinity. Our mean was 18. The standard deviation was 3.2. And we're going to end up with roughly 1.435%. Now, when you did the normal CDF from 25 to infinity with a mean of 18 and a standard deviation of 3.2, that should come back as 0.01435. Okay. But the problem here asks for the percent chance, or what is the percentage of times that a backpack is more than 25 pounds. So that's where we want to turn this into a percentage. Okay. So we need to multiply that probability that we get from the normal CDF by 100. Okay, so now we're going to do a percentile problem with the backpacks again. So we want to know how much do the lightest 25% of backpacks weigh. Okay, so we're going to draw a normal curve, mean of 18, because the average weight is 18 pounds. Okay, so we want the lightest 25%. So we're looking for a weight that separates the bottom 25% from the top 75%. We're going to use our inverse norm. We have to tell the calculator the area to the left, which in this case is 0.25. So it's going to inverse norm, 0.25, mean of 18, standard deviation of 3.2. And when we do this, we're going to get approximately 15.842 pounds. So what this is saying is 25% of UT students' backpacks weigh 15.8 pounds or less. So let's look at a third variable. Okay, so here we're talking about the volume of a Starbucks Grande Latte. Okay, we're going to assume they're normally distributed with the mean of 16 ounces and a standard deviation of 0.25 ounces. So if this is the case, we want to know the probability that a randomly selected latte is going to be between 15 and 16 and a half ounces. So, one more time, normal distribution. So we're going to graph 15.5 and 16.5. We want the area in between. So to find that probability that the volume is between 15.5 and 16.5 fluid ounces, we're going to do our normal CDF between those two numbers, plug in our mean, plug in our standard deviation, and this says there's a 0.954 probability that a randomly selected Grande Latte will be between 15.5 and 16.5 ounces. So for my last example here, we're going to stick with the Starbucks Grande Lattes, okay? And we want to know the middle 90% of Grande Lattes have how much liquid in them, okay? So this is a percentile problem, but it's actually two percentile problems because we need a cutoff, all right, for the beginning and the end of the middle 90%. So again, I'm going to draw a normal curve with the mean of 16. We're looking for what volume, how many ounces separates the bottom 5%, and how many ounces separates the top 5%, so that in between those two cutoffs, we get 90% of our values, or our Grande Lattes. So I'm going to start over here on the left side. Okay. Again, we want to find our X, right, our ounces, so we need to use the inverse norm. And to find our lower limit, we want to find the area to the left. We need it to be 0.05. So I'm going to do inverse norm 0.05. Okay. 16 for the mean, 0.25 for the standard deviation. So that's telling me my minimum, all right, is 15.589 ounces. Now to find our upper limit for the middle 90%, okay, so that's our right cutoff over here, separating the top 5% from the bottom 95%. Now the inverse norm requires the area to the left, so I'm going to do inverse norm of 0.95, okay, and that's going to get me 16.411 ounces. And so that is going to be the volume that separates the top 5% from the bottom 95%. Put these two together, and what we have is that the actual volume of the Starbucks Grande Latte for the middle 90% is going to be between 15.589 and 16.411 ounces. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!